Hi, my name is Hang Jiang. This is my latest paper revisiting the first-order approach to principal agent problems. The paper studies a classical incentive problem with moral hazard. Model for this problem is developed by Nobel Prize winner Ben Holmstrom in 1979. In this model, a risk-neutral principal hires a risk-neutral agent to perform on some tasks with a limited liability contract as X, where X here is the outcome. And the limited liability means that the compensation to the agent should be non-negative for any outcome. Outcome X here is influenced by agent's effort A, but it is unobservable to the principal. The principal can only observe the outcome X. We assume the distribution of X is fxa, which is twice differentiable in A, and its density function is also differentiable in A. The agent's cost function is denoted by VA, which is increasing, convex, and differentiable in A. So based on this model setting, the agent's expected utility can be represented by this expression EAAS here, and the principal expected utility can be denoted by EP. Given a contract in this example, the agent chooses an optimal effort A that maximizes his expected utility, and the agent we also should require individual rationality that optimal expected utility must be at least his residential utility U0. This is also the outside option of the agent. So based on this kind of this setting, the principal selects an optimal contract to maximize her expected utility. And naturally follow this model setup, the principal's problem can be formulated using this OP program here. And this program is actually very hard, and economics has been working on this problem for decades. The main difficulties for this problem lies in two parts. First, the IC constraint here, which is the argmax expression, is basically an infinite set of constraints because argmax is equivalent to infinite many inequalities. The second hard part is infinite dimensional decision space. The contract SS here is a general non-negative function, which means the decision space is infinite dimensional and the function is from a general function space. So traditional optimization methods, for example, linear or nonlinear programming, calculus of variations are not applicable to such uncountable setting. So the model here remains unsolved in the general sense. To handle this problem, literature usually choose to solve the relaxed problem. They replace the IC constraints with the following RIC constraint, and RIC only restricts agent's choice to be stationary point, but the IC constraint restricts agent's effort to be global maximal point. We know that these are not equivalent. So they assume that the first order approach is valid, which states that any optimal contract to a relaxed problem is also optimal to a regional problem. But this is an indulgence assumption, so they further found exogenous conditions that justify the first order approach, namely the Merlis-Rosen condition. And this is established for a strict risk averse agent. So in a risk neutral setting, it is not necessarily hold. But many literature in the risk neutrality and limited liability uncountable case invoke this condition to justify the first order approach. And now we show that this is actually not correct. And the Merlis-Rosen condition does not imply first order approach and a risk neutral setting, which means most of the literature are wrong. So we give a counterexample here to show that we can find a contract that is optimal to the relaxed problem, but suboptimal to a regional problem. And further, we provide a different solution approach to solve this problem. And the solution approach is based on a very important finding here. We find that optimal contract for a relaxed problem is always a simple contract, simple Quadrant-Balance contract. Quadrant-Balance contract is defined by a very simple step function here, as given here. If the outcome exceeds a certain level Q, then the agent will get a bonus B. And we show that it is sufficient to focus on Quadrant-Balance contract for a relaxed problem because any feasible contract in the relaxed problem generates certain results can be replicated or can be matched by a Quadrant-Balance contract. So based on this observation, we show that it is sufficient to focus on Quadrant-Balance contract for a regional problem under some general conditions. So this is how we solve the problem, and we show that under our conditions to solve the original problem, it is without loss of optimality to solve this simple two-dimensional and three constraints program. And now our conditions also very, very general. So this is a short version of this paper. And to get a full paper, please scan the QR code. Thank you very much.